So we're going to do another example of utilizing Newton's second law. And I kind of vaguely drew this little system over here where we have a two-mass pulley system. And I went ahead and wrote down all the givens. So we have one block being kind of suspended in the air. We have another block here up on the ramp, and there's a force being applied to it at an angle. And we're given the masses, we're given the force, we're given theta, and we're given the coefficient of friction. And we need to do a handful of things. But the first thing I'm going to do is I'm just going to draw this force vector out really quick. So this is theta. This is our force vector. This is the force in the y direction, which is just F sine theta. This is the force in the x direction, which, just doing right triangle trig, is F cosine theta. So I just wanted to draw this guy in all its glory out. Okay, so let's get into what we actually need to do. So part A, this would be kind of like an exam-like question, good study problem. First, find the normal force. The normal force on 1. Well, the first thing I would do is probably draw a free body diagram for 1. So for 1, let's see, what do we have going on? We have a force due to gravity, or weight force, which we know is just equal to m1g. We have that normal force that we're so interested in. We have a tension force from the rope. We have a force due to friction. And we have that push force going on at a little bit of an angle. And this force to friction, if it looks kind of weird, that's just, I'm trying to draw it not right over tension, but it's not at a weird angle like that. Okay, so now after that, what we should do is get into Newton's. Let me give myself a little more space. Newton's second law. So we're interested in the normal force, which is in the y direction. So the sum of forces for 1 in the y direction is equal to mass 1 times acceleration in the y direction. Now if we go up here and we look at mass 1's not bumping up and down. There's no acceleration in the y direction. So this is 0. Now, what forces are acting in the y direction? We have a couple. We have a positive normal force. We have the positive component of the force being pushed, which we know is just F sine theta, and minus the weight force, which is just m1g equals 0. Or the normal force is m1g minus F sine theta. And there you go. If you plugged in your values, we know the mass, we know the magnitude of the force, we know gravity. We know everything we need to know to solve this. I'm going to keep it as just an expression, but that's what we need. Now, part B says find the acceleration of the system. So what we mean by that, if we look up at the picture, they're only going to accelerate if one of the other ones accelerates. They're proportional to each other. So if mass 1 just stays in place, mass 2 is going to stay in place. If mass 1 is going to be pushed along that surface, M2 is going to be pushed up at the same acceleration that M1 is being pushed across because they're connected to the same rope. In other words, the acceleration for block 1, which is in the x direction, is equal to the acceleration of 2 in the y direction, which I'm just going to call A. Kind of put that in not the best spot, but hopefully that makes sense. So that is going to be needed for us to work through it. Now what I'm going to do is I'm going to draw a free body diagram for the second block, which isn't too hard. We have tension. We have the weight force, which again we know is equal to m2g. Just so we know, this is mass 2. This is for mass 1. Just so we don't get them confused. Probably really shouldn't, but whatever. Okay, so now we'll do Newton's second law again. Newton's second law. We've already done it in the y direction, and we've exploited that for the one unknown we don't know, which is the normal force. So let's look in that x direction. So the sum of all forces for 1 in the x direction is equal to mass 1 times acceleration, which I'm just going to call A because of what I said earlier. So now acceleration doesn't go away. We have some acceleration. So what forces do we have acting in the x direction? Well, again, we have a few. We have positive F cosine of theta, which is coming from that little push. And then what do we have? We have minus tension and minus the force due to friction is equal to M1A. Okay, well, that's all fine and dandy, but we're interested in M1A. Now, I'm going to rewrite this a little bit. F cosine theta minus tension, which we don't know tension yet, minus what you need to know is that the force of friction, kinetic, is equal to our normal times our coefficient of friction. Turn my light on there. You'll need this for every time there's friction. So, more than likely. So I'm going to replace that with this. Normal coefficient equals M1A. Now, what I want to do, I don't know tension, and I don't know acceleration. I have two unknowns in this one equation. So what I want to do is, you guessed it, Newton's second. Again, but this time for mass 2. Now, the only thing ever happening with mass 2 is in the y direction. So, sum of all forces for 2 in the y direction is equal to mass 2 acceleration in the y direction, which again is just A. The forces, we have a tension force minus the weight force, which is M2G equals M2A. Or tension, if I add M2 over and factor that out, is just M2 plus G times acceleration. So now I'm going to take this and plug that into here. So I still have the F cosine theta minus tension, so that's going to be minus M2G minus M2A. I distributed the M2. Hopefully you're okay with that. Draw that a little nicer. Minus normal, again, we can replace this with what we found with part 1. Normal is M1G minus F sine theta. So let's go ahead and substitute that in because those are all knowns. So minus normal, so minus M1G minus F sine of theta, so that's F sine theta. Actually, let's do this. Better idea. minus, let's put the coefficient of friction out here. And then in parentheses, we'll just do m1g minus f sine theta, because that's just a number. We don't need anything out of that, which is m1a. We really want to get the a's on both sides, so let's add m2a over and then factor it out. F cosine theta minus mass 2g minus our coefficient of friction times m1g minus f sine theta equals m1 plus m2 times a, and then finally just divide everything by m1, m2. So acceleration is equal to f cosine theta minus m2g minus kinetic coefficient of friction times m1g minus f sine theta, all divided by m1 plus m2. There's our acceleration of our system. That's all we need to know. So then, hopefully that makes sense. The big key was knowing this acceleration trick that we did up here, and then we just have to look at Newton's second law, solve for things we know, and it comes together nicely. Part C wants us to find tension. Find tension. And we know tension is equal to m2 times g plus a from up here. So now that you know a, whatever value this is, you can plug into here and you'll get your tension. I'm not going to replug it all in because I don't think it's necessary. I think you guys get the idea. We kind of already had to do that. Part D, this is the last part. What mass for M2 keeps the system from moving? So keeps the system at rest. Okay, so again, we're going to do a whole bunch of Newton's second law. It gets tiring. So, from the free body diagram of 2, what do we know? Well, we know that tension minus m2g equals mass times acceleration in the y direction. That is from here. That's this. The only thing is, we're not saying that this is 0 now. Or I'm sorry, we're saying this is 0 now. My apologies. So in other words, tension equals m2 times g, or tension divided by gravity is equal to mass 2. So that's what we're looking for, mass 2. We're going to have to do more of Newton's second law, though, because we're not sure what tension is. What we want to do is go back to the x direction from 1. And instead, we're just going to say that acceleration is 0. So that is this guy. And this time, we're going to say acceleration is 0. So that's just... And we're setting the acceleration equal to 0 because they're stationary. Hopefully, you guys are okay with that. Minus normal times this minus t equals 0. Now the normal force won't change because there was never any acceleration in the y direction. So I'm just going to substitute our normal force in, and we get tension equals F cosine theta minus, so I'm going to try my best here to factor everything out. I'll just say this, minus m1g minus f sine theta. We'll put the mu naught k here. And then this can be plugged into here. So F cosine theta minus coefficient of friction times m1g minus F sine theta, all divided by gravity, is the mass 2. And there you go. So that was an exam-like question, 4 parts, requires a little bit of work. That's all there is to it. Hopefully that makes sense on how we did